All right, so to recap where we were on Friday when we left off, this is a particle motion question. Like I said, we'll have a full section devoted to that, but particle motion is the same thing we do in any other sort of context problem, but things just have different names. So what we had was a graph of velocity. That is probably the most common thing that you'll have. Because if you go back to the beginning of the year when we took the derivative of this graph, we found out the acceleration. But now that we know how to integrate, that's what we're focused on. And we're going to integrate velocity to find the change in position or the displacement of the particle. So that's what we did in letter B. We did just the integral by itself from basically the way it was defined was we had an accumulation function. So an accumulation function locks in our starting point. It's saying we're starting at t equals 0. And then the thing that we're going to plug in is our ending point. So we found the d of 5 to be 2, which meant that the particle was 2 units to the right of where it was at time t equals 0 at t equals 5. So we plugged 5 in to figure out where we were different from where we started from. That doesn't mean that the particle traveled 2 units. It could have, but it's not guaranteed that the problem traveled 2 units. It could have done 3 to the right and then 1 back to the left. It's sort of just like the net distance traveled. So where it was in relation to where it started from. We did also do that by plugging in -4, which gave us a situation where our limits were quote unquote backwards. We had a bigger number on the bottom and a smaller number on the top, which can happen. This was a situation that I kind of set up where why would we have negative times? Because somebody didn't hit the timer until 4 seconds into the experiment. So we were actually going back in time to figure out where the particle was when it started, not when the timer started. And any of the signs is all taken care of by the integral. This is a -10 telling us that the particle was 10 units to the left of where it was at time 0 when it started to move 4 seconds before the timer went off. And that's all taken care of with the integral. You don't have to, think about forwards and backwards. It was to the left at -4. It was at the left 10 units where it was, from where it started at time equals 0 when it started at time -4. A lot of little details there, right? I kind of got lost in my head on that when I was explaining. Okay, so letter C. This is the second type of problem. There's one more complication to this. If the position is 5 when the at time t equals 0, we did not know any positions. We just know where they were in relation to each other. So if x of 0 is 5, what's the position of the particle at t equals 3 and t equals -2? We have to take the starting position and then add the change. So we want to find 2 things. We want to find x of 3, which would be the position at time t equals 3. So we're going to start with the position at time t equals 0 because that's the only position we know. And then add the change over that time period from 0 to 3. And when we integrate velocity, that tells us how much change happens as a result of that velocity. So this is going to be that 5. X of 0 is 5. And what is the integral from 0 to 3? Not 3. That's from 0 to 1. Oh, you're right. Because then these 2 guys cancel out, don't they? Yeah. Yep, they do. You were right. Sorry, I jumped the gun on the no on that one. Yep. So yeah, you do 3 plus a half minus a half. So 5 plus 3 is 8. All right. Same thing with the other one. We've got to find x of -2. What was its position at time t equals -2? Well, that's our starting position plus the integral from 0 to -2 of v of t dt. And like I said, the integral takes care of the fact that we're actually going back in time here, right? The question I'm really asking is, where was that particle 2 seconds before you started the timer? But you can just add that as long as basically this starting position matches the starting position of the integral, it will take care of any sign changes for you. So this time we're going to do 5 plus, what's the integral from 0 to 2, negative 2? Say it. Negative 6, because you're traveling backwards. So those, when your limits are reversed, you're going from a bigger number to a smaller number, all of a sudden area above the curve is negative because your heights are positive, but your widths are negative. This is a negative 2 by 3 rectangle. So we've got 5 minus 6, which is negative 1. Cool. All right, questions on that? Okay. All right. So last but not least, some calculator active problems. No, but not last but not least. This kind of, we're going to switch over to something different on example 4. Okay, so this is kind of taking what we did in that last problem, but taking it out of taking it out of context. So it's just, I have a function value, I have a derivative, and I want to know what the function value is somewhere else. We've done these problems before with fundamental theorem, but now we're going to kind of look at them with the idea of an accumulation function. If I know that f of 5 equals 9, the accumulation function that I'm thinking about is this, the integral from 5 to x of f prime of x dx. This is the accumulation function that's going to help us out. We're just going to replace the x with whatever we need. So if I want to find the f of 8, I'm just going to take the f of 5 and then add the integral from 5 to 8 of f prime of x dx. The integral of f prime tells how f changes based on that rate f prime. And that is 100% calculator active. I'll go over to Desmos. I'm going to put in my, unfortunately, I've got to label it f of x. It is, I actually have this packed on my desk, sine of 3x minus 7, but squared. So I've got to actually do, in parentheses, it always gives me 2 sine. I said in parentheses, but the parentheses never hit. There we go. Sine, another parentheses. Did I say 3x minus 7? Yeah, thank you. But squared, so I want to square the whole sine, so I'm going to do it that way. So now I have a blank copy of this packet sitting right here. So instead of asking and guessing and flipping back, basically all I have to do is 9 plus the integral from 5 to 8, like I said, make sure I get those numbers right, of f of x dx. And I'm good to use. And I'm good to use f there because I'm not using x anywhere else. That same thing can, but I had to label it. I'm not allowed to label this f prime. So it is f prime on your paper, but in my calculator, I have to just call it f. Because I can't say f prime of x equals, it doesn't let you define a derivative. Yeah, now that's a Desmos limitation. Sometimes what I'll do is this, to just, if I don't want to confuse myself, I'll just do it like f underscore prime. I just don't know where the underscore is. I don't know where the underscore is on this keyboard. I don't see it on either spot. Huh. Yeah. Yeah, so I mean, you could subscript that F. You could just use a different letter, but it's a good question, and it's just an absolute limitation of Desmos because it treats F prime as you want me to find the derivative, not I'm defining the derivative. Okay, using either your calculator or a Desmos, you try that second example. Do this. Oh, that's yeah. I don't have Wabbit on this one. No, as long as you keep. That's why I was saying earlier that as long as you keep the limits correct, it should be the f of 5 plus the integral from 5 to. And that like the integral takes care of whether you're going backwards or forwards, which is nice. The exact same way I have it here, only you'll be putting that into your integral. Alpha F2, I think. Alpha F2 or alpha F3. No. I mean, you got to type in the first part, but you want, yeah, number 4 function in. No, you have to put sine of 3x minus 7 squared. Yeah. Yeah, I don't know. I mean, Desmos is easier, but if you guys really want to do a calculator, go for it. Your Chromebooks, Dad. I thoroughly agree. Do you disagree that her Chromebook says? Disagree that Desmos is easier. I mean, it's a million times easier. I got my answer down. Probably take you. Well, now it'll take me a second because I've already got everything typed in. 9 plus. Actually, it'd only take me a second because all I have to do is change the limit. I don't even need to retype it again. Boom. Limits or bounds. They're both, yeah, bounds probably the better word. I tend to call them limits. It is 1. Was I going to 1 or negative 1? What was the question? 1, yeah. Yep. So you better get that answer if you want to be correct. That might be another good. Got it, yeah. Yeah. Yeah, so the x value that you're starting at should be the lower bound, the lower limit of your integral. That question, to answer both parts of that, it's just one button click. And even in your calculator, if you had the first one in, you could just go back and grab it and pull it out. Go back and grab it and just change what you had. So you've got 7.058. We will write that in. I guess I never wrote the answer here. What was the answer with cool. All right. Okay. So that's no different what we were doing with fundamental theorem, but you guys kind of had to add and subtract. You had to do some algebraic manipulation. This is the way you do it. If you know one value, start there and then start your integral there and go to wherever you want. The integral takes care of forwards and backwards. Okay. So what we're leading up to, I kind of needed to introduce what an accumulation function was, but now we're going to get to this second fundamental theorem, which kind of has, 2 parts to it. We're going to kind of explore that finally using our colored pencils here. I do want to explain everything that's going on here. So we have not just an accumulation function, we have a group of accumulation functions. We're looking at 4 accumulation functions where what I've done is I've changed that starting boundary. Yes, sir. Oh, you're done. Okay. All right. Starting limit. I just said boundary. I added a new word to it. So the f sub negative 2 of x is the accumulation function where the lower limit is negative 2. The f sub 0 of x is the accumulation function where that letter a is 0. One property that will definitely help you out with these problems is if I've got the f sub 2 of negative 2, and I then want to know what that f of negative 2 is, that is essentially putting the same thing in the lower limit and the upper limit, right? So f of negative 2 has the lower limit of negative 2. When I plug negative 2 into it, that's also negative 2. What does that integral evaluate to if it has the same limits? 0, right? So we're going to have a 0 in each one of our tables. That 0 will be here. In the next table, it will be at 0 because that function has a lower limit of 0. This one will have it at 2, and this one will have it at 4. And essentially, that's kind of where you want to start at with integrating. So when I do this first function, I know that I have a value of 0 at negative 2. So when I want to know the value at 0, all I have to do is integrate from negative 2 to 0. And what's that area that I have highlighted there? 5. Yep. You didn't, but Nate did. Sometimes other people answer. Okay. So that area is the total area because the capital F of negative 2 was 0. So the change in that area is also the value of the function. So then we'll go to 2 and we will add on how much more? 3. So our total will be 8. And then at 4, we're going to add on how much? 1. Yep, that'll give us 9. And then when we get to 6, what are we going to do? Subtract 1, correct, to give us 8. Cool. Okay. So with one of my colored pencils, that was supposed to be an eraser. So with one of my colored pencils, I'm going to go ahead and graph those 4 points. 0, 5, 8, 9, 8. So 0, 5, 8, 9, and 8. And we're just going to go ahead and draw a nice little curve through those things. All right. So now let me get you started on the second table, and then I'm going to have you guys finish the rest of it. All right. So now this time, my 0 value is at x equals 0. So what's my function value at x equals negative 2? Correct, negative 5. And that's because I'm integrating backwards. I'm starting at 0 and going to negative 2. So although my heights are positive, my widths are negative, giving me overall negative. All right. So your job right now, one too many, baby bathwater. Threw the baby out with the bathwater. I got rid of my... All right. Your job is to fill in those tables, different color for each one. Doesn't care. I don't care what color the numbers are. Different color when you graph them. I got you. It's fine. Yeah. Yeah. Should really have those tables go to 8. I don't know. We didn't finish the graph. It would just be, they actually aren't exactly parabolas. It's a parabola up until it's spaced between 6 to 8. But then because that weird shift in the line would cause it to still be, it still acts like a parabola, but it's just a different parabola. It's kind of like 2. It would still go down, but it would be, would actually be it would be the start of a concave up parabola.
Yeah, that makes sense.
Yep. Yeah, because the function little f is increasing. Yep. All righty. All right. So what you should notice as you're doing this is that the tables have a consistent increase. We're increasing by 5. We're increasing by 5. Then we're increasing by 3. Then 1. And then 3. It's just where we're starting. Oh, 3, and then minus 1. It's like consistent increase, decrease. So following that pattern, your second set of numbers should be 3, 4, 3. Yay? Okay. So now we have to back that pattern up. We've got to take away 3, so negative 3, take away 5, negative 8. And then it should be 0, 1, 0. And then our last one should be negative 1, negative 1, negative 4, negative 9. Am I right? Okay, cool. Yeah. They've got consistent changes vertically, and they also have consistent changes across. So like every number in this table is 5 more than every number in that table. So anyway, not that all of that is super, super important, but that is what's going on there. And then when we graph them, is we do end up with the same shape no matter where we are, right? Yes. It's just a vertical shift of one another. So this one starts out at negative 5. But again, it stays a consistent 5 below. So it's 5 below there. It's 5 below there. And then our green is just 3 below. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. And then our final purple is just 1 below. Boop, 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 boop. Yeah. Okay. All right. Where's the relative max of capital F, no matter which capital F you're looking at? Which x value do they have their relative max? X equals 4. What's the value of F at x equals 4? Little f, sorry. Little f is 0, right? Oh, we've got a relative max, and then some other function has a value of 0. That sure sounds like the derivative, doesn't it? When is your function increasing? When is capital F increasing? Same sort of question, before 4, right? And isn't that when little f is positive? Correct. And then when does little f start, or big F start decreasing? The functions you do started decreasing after that 4, right when little f started decreasing. So this is the relationship here. This picture is the fundamental theorem of calculus. The blue line thing that I have graphed there is the derivative of the curves that you are drawing. So let's fill in our notes and then look at the fundamental theorem of calculus. The functions you drew an example for differ only by a vertical shift. Each of the accumulation functions that you drew has f of x as its derivative. That means that each one of those capital F of x's are an antiderivative of f of x. I feel like when I wrote these notes, we hadn't used the word antiderivative as much that year. So that's why that's there. Derivatives and integrals are inverses. That is, they cancel each other out. You got to be really careful with that line there. It's not always a perfect cancel out. We need to be working with an accumulation function in order for it to be a perfect cancel out. Okay. Which leads us to the fundamental theorem of calculus, which says that if you take the derivative of an accumulation function, you are left with the function on the inside. But that function you're taking a derivative of has absolutely got to be an accumulation function. You did 2 cards this morning. The easy part is the accumulation function. This is the type of thing that it's like, there's nothing to learn here. Oh, I need the derivative of this? Well, just get rid of all this stuff and rewrite the function itself, right? There's just it's, a question that tests this is super simple. Take a look at what I mean when we do example 4. Find the derivative of each function. Probably. Find the derivative of each function. Letter A, is capital F of x an accumulation function? Does it start at a constant and end at just a variable? Yes. So what is f prime of x according to the second fundamental theorem of calculus? Cosine 3x. Did I have to use any chain rule stuff there? No. No chain rule stuff, none of that when you're working with an accumulation function. It's just too easy. Letter B, is capital G of x, tricky question, is capital G of x itself an accumulation function? No. But is the second part of it an accumulation function? Correct. So G prime of x is the addition of 2 things. Derivative, what's the derivative of 0? What's the derivative of 3? 0. And then the derivative of that accumulation function from 0 to x of 2x minus 5 is just, too easy, 2x minus 5. That example is just to show the vertical shift. G of x is a vertical shift of an accumulation function. So they all have the same derivatives. It's just 3 higher than the given accumulation function. An important conclusion that I mentioned here, but I know sometimes shows up in questions, is we are saying that capital G of x is differentiable by basically writing it as an accumulation function. As long as the function on the inside is continuous, then G prime exists. So if I wanted to know if capital F of x is differentiable, yes, because cosine of 3x is continuous. F prime of x has values everywhere. There's never a time where you won't be able to get a value for f prime of x, which means that f prime of x always exists. So capital F of x is differentiable because this is continuous. Same thing here. Capital G of x is differentiable because 2x minus 5 is continuous. It's not always that easy. We don't always have accumulation functions. Sometimes the thing in our limits isn't just an x. Sometimes it's a function, 2x, 3x, x squared. It's a little bit more complicated with these functions. They don't have names. We have to just follow the rule with them, okay? So here's how it works when you don't have an accumulation function. You've got something else going on. You're usually going to be in one of 2 situations, but there is always, of course, a situation where you have a constant in the numerator as well. But it works no matter what. Let's look at the general formula, the bottom one, and then we'll go back up and see how that's the same as the top formula. So there is some chain rule involved in this one. We are going to follow this is going to mirror what we do when we do the regular fundamental theorem of calculus. We're going to need to plug those limits into our function. So we're going to actually have f of g of x minus f of h of x. But there's some chain rule that goes on here, and it's actually g prime of x times f of g of x and h prime of f of h of x. So that is not nearly as easy of a formula. The chain rule comes from the limits, not the function itself or the bounds. That's where the chain rule part is. You also then need to plug those things into your function. This is a general form of the second fundamental theorem that we just learned. We're going to kind of work our way backwards to an accumulation function. What happens if I put a bottom limit as a constant? That's what we'll write here. And then we'll think about what happens if this isn't g of x, but it's just x. And we'll see that this formula is consistent no matter what you have. So let's say we didn't have functions in both spots. Let's say we are back up in this upper level where the lower limit is just a constant. Following the formula, I still have g prime of x, f of g of x. But then to that, I would subtract, starting with a prime, but a is a constant, right? So what's the derivative of a constant? So that's why that's gone. There is nothing there. You don't have to worry anytime there's a constant. Okay. And last but not least, think about the accumulation function where I don't have g of x there, I just have the letter x. What if g of x is just x? What is x prime? 1. So that's gone. And then this just says f of x, which is the fundamental theorem of calculus up at the top. So these formulas are consistent with each other. You can take this general formula and work back to the formula above it, and then the formula on the previous page. Okay, so let's try some examples. It does look like A and B use the top formula and C and D use the bottom formula. So the example says find f prime of x, capital F prime of x equals, I need to take upper limit first, just like when we're evaluating an integral, and I need to find the derivative of that upper limit, or that upper bound. So what is the derivative of x cubed? 3x squared. So this starts out with 3x squared, and then we leave the function alone because derivatives and integrals cancel. I shouldn't say we leave it alone. We're not going to take any derivatives of our inner function because derivatives and integrals cancel each other out, but we are going to change the argument. It's going to be sine of the limit, so x cubed. Since the lower limit is constant, I'm done, right? If you integrated this to negative cosine, plugged x cubed and plugged pi over 2 in those using the regular fundamental theorem, and then took a derivative correctly, you'd get right here. Okay, so this is saving us 3 steps because to do this otherwise, I'd have to do negative cosine t, evaluate it from x cubed to pi over 2, and then take a derivative. And in taking that derivative, the chain rule would tell you to take the x cubed and bring it out front as 3x squared. Letter B, I don't know what my function is. It's not sine of t, it's h of t. That doesn't matter. F prime of x. Yes, 4 times h of 4x. Sorry, I have to change colors. So it's going to be 4, because that's what we do chain rule on. And then the h of 4x, because we plug those bounds in. Just trying to color code that quickly. Boom. And the blue shows what changed. For C and D, our f primes are going to have 2 parts because both limits are not just plain old x's. So it's going to be something minus something. Chain rule on both parts, 3x, 2x. Oop, that's a big one. Guess that's fine. So upper limit first, just like regular, we're going to do the derivative of 3x is 3. And then we are going to take that 3x and plug it in for t. So we are going to get the quantity 3x squared, that's important, minus 3x minus 2, and it's going to feel exactly the same. 2x squared the quantity minus 2x. And then last but not least, letter D, same deal. So that upper limit is an x, so when I go to do chain rule on that, that's just going to give me a 1, right? 1 times 5x. And then we're going to minus, because again, this is just like the fundamental theorem. The derivative of negative x is negative 1. So that's going to end up being negative 1 times 5x. Yes, thank you. It'd be 5 times negative x. Yeah, it does equal 0, doesn't it? So we end up with 5x minus 5x. Is 0. I think if you evaluate that derivative, you actually get a constant, which is kind of why this happens like that. So we end up with 5x minus 5x equals 0. All right. I have to think that one through. Okay, still have 10 minutes. Not bad. We did lose time on Friday. This was kind of designed to get through the drawing on one day and then do this stuff on the second day and give you guys time to practice. But we had a snow day, unfortunately. At least 2-hour delay. So yeah. Be careful when you get to the second page of the practice. You have to ask yourself, do I have an accumulation function or not there in each of those sections? But some of those problems just answer themselves. Like 3, 4, and 5, 6, they all just answer themselves. Stop.